Hi all. In this video, we're going to talk about some more examples of double integrals. Let's go ahead and jump right in. So the first one we have, we want to set up the double integral over the region D. The region D is given in this graph here. So let's go ahead and highlight that. This region here of some general function f of x, y, and it asks us to set it up as both a type x and a type y. So let's go ahead and do type x first. Remember what that means is we want to think about doing it as x first. So that tells us we want to move parallel to the x-axis when I'm finding those inner bounds, and I want to do an x equals for my first bounds. Okay, so what does that look like? I'm doing the x first, so I've got my dx on the inside. That's the first one that we would evaluate. I'll go ahead and just put the function in, f of x, y, and then we need to find those x bounds. Maybe we'll do these x bounds here, the dx bounds, we'll do those in green. So I'm going to find my x bounds. And then outside of that, we'll do our dy. Those y bounds are just going to be points because they're on the outside. But the inner bounds, the x bounds, have to be curves or lines. So we don't want to think of just constant values, but curves or lines. So how do we find those curves or lines? We're going to move parallel to that x-axis. I'm going to do that in pink. So my x-axis moves left to right. So I'm going to draw a bunch of lines moving parallel to the x-axis. And I want to think about the first time that those lines hit into my surface. So each one is going to hit into the surface sort of further and further along. But where they hit into the surface is always along this blue line. And that blue line is y equals root x, but because I'm in the x-axis, moving parallel to the x-axis, I want x equals stuff. So I change that to x equals, squaring both sides, y squared. So that bottom curve is x equals y squared. Then each of those pink lines moves into my region. It's moving through. We can kind of think of it as like a toothpick moving through, poking through there. And it leaves in these different spots. All of those different spots where it leaves the region is along this green line, y equals x squared. We have to change that to x equals for my x first. So I change it by square rooting both sides to get x equals square root of y. So I'm going from x equals y squared, that's my blue curve, to x equals root y is my green curve. Then my points, I'm actually just going to look at the smallest and biggest point in the y-axis. So I'm going to take those points where they intersect, where I start and end, just find the values, just the numbers on the y-axis, and that was 0 to 1. So I get 0 and 1 for those points. To do type y, we're going to do sort of the opposite now. We're going to think about moving in terms of the y instead of in terms of the x. So for type y, that's my y first. So I'm going to move parallel to the y-axis. And I'm going to think about y equals. Again, this is just for my inner bounds here, that dy bound. And then after I do that, I'll do my dx bounds, but those dx bounds will be in terms of just points, so just values there. So points on the outside, curves on the inside. We still have that general f of xy function. All right, so what are we going to do? I'm going to redraw my picture real quick. I have that y equals x squared and y equals square root of x as those bounds. I'm thinking about this region in between here as my D. But now, instead of moving left to right, I want to think about sort of poking my surface bottom to top and thinking about where I intersect for there. And I see if I send a whole bunch of lines parallel to that y-axis, the first time I hit my surface is always along this green curve. That's the one that's on the bottom. That green curve is x squared. Then each of those lines is going to go through my surface. They're going to leave along this blue curve. That blue curve is y equals root x. Again, I'm doing the y equals version because it's the type y. Those are my inner y curves. And then for x, I'm just looking at points. I find the biggest and smallest points along the x-axis. Those two curves are going to intersect at 1, and so I get 0 to 1. If you're having trouble with these curves, I posted a separate video that talks about the different curves that you'll need to know how to sketch for these sections, so go ahead and check that out. So what we've done here is for my two different integrals, I set those up. I did a type x, where I did x first. I had x equals curves. In terms of y was the variable that came later, so I was allowed to have y's in my bounds. And then on my type y, I did y equals bounds in terms of x. X came later, so those were allowed to be in terms of those bounds. They look very similar to each other, but one of them is going to be that x first integral, and one of them is the y first integral. All right, let's do a bit more practice with these. In this one, again, we want to switch the order of integration. So for me, the first step that I would do here is to draw out the region that we're integrating. And so let's think about what we have. I have an x first integral here. So my x bounds are going to be x equals 0 and x equals 4 minus square root of x. So if I were to start to draw this, x equals 0, that's just along the y-axis. But I know that I don't have just a single point there. I have that whole line, y equals 0, because that was the inner integral. And we can check sort of to kind of help us out. I'm going to fill in also the y goes from 2 all the way down to negative 2. So it tells me how long I should draw this curve. So between 2 and negative 2, I'm drawing x equals 0. There's x equals 0. So if you want, you can not draw it up above, but that's fine. You know it stops down there. And now we also have x equals the square root of 4 minus y squared. It's helpful to recognize curves of this type. The easiest way to recognize it is to square both sides. X squared equals 4 minus y squared. And then we add over that y squared. And we should see that this is a circle of radius 2. So whenever you see sort of x or y, so x equals the square root of some constant minus y squared, or y equals the square root of some constant minus x squared, we should see that as half a circle. Why is it half a circle? Well, because I have x, but it's only the positive square root. So I'm only getting the positive values of x in my circle. So I have this entire circle of radius 2. Here's where x equals 0. And so x is positive on that side, and x is negative on this side. So let me not put in the, let me actually just highlight the part of the circle, not the shaded part. This side is where x is greater than 0. And that's what I have here. So I have this circle of radius 2, but only the side where x is bigger than 0. So the region of integration I have is the region starting at x equals 0, going to x equals the square root of 4 minus y squared, that nice circle there, between y equals negative 2 and y equals 2. So it's half of that circle. So now if I want to switch the order of integration, my function stays exactly the same. I'm going to do dy first now and then dx. So my y, I'm going to move parallel to the y-axis, bottom to top. I enter into my surface along this curve down here. I'm going to color it differently. I'm going to make it orange. So I'm entering along this orange curve. I go into the surface. I'm hanging out inside, going straight up parallel to that y-axis. And where I leave is along the same curve, but now the top half of it. So I'm leaving along this part that I'm coloring into green. So I'm thinking sort of here that I'm going from orange, the bottom half of that circle, up to green, the top half of that circle. And then for x, the smallest value of x, I'm just looking for points here. So the smallest point on the x-axis I see is 0. The biggest point on the x-axis, we know that's 2 because this is a circle of radius 2. So I can't just write green and orange. I actually need to find equations for those. Because it's a y first integral, I needed to do y equals. So I need some y equals equations for that green curve and that orange curve. Now I know that those green and those orange were exactly this x equals the square root of 4 minus y squared. That's where we drew. We knew that that was the same as x squared plus y squared equals 4. And so for when I solve for y equals, I'm going to get y squared equals 4 minus x squared. And then I take the square root of both sides. What do I have to remember when I take the square root? I have to remember my plus or minus. And so the bottom part is the minus. That's that y equals negative the square root of 4 minus x squared. And the top part is the plus. That's the y equals positive the square root of 4 minus x squared. And so my upper bound is 4 minus x squared, and my lower bound is negative 4 minus x squared. You don't need to put the y equals if you don't want to. We could leave off those y equals. We could just put negative 4 minus x squared and positive 4 minus x squared. That's up to you. And so that would be what we get for the integral. So what does the double integral of 1 give us? We've seen this a little bit before, but let's go ahead and remember. If I have some region D in my xy plane, so D is sort of down here, and I'm integrating the function 1, then I'm going up to this height of 1 for each of my spots. I'm going to make it kind of look like a D so we can remember. And so I get this shape, which is just some region where I've got some base area down here, and then my height is 1. If you remember, this is a geometric formula. If I have some region, some solid, where the height is always the same, so it's some geometric area which is all pulled up to a height of 1, then the volume is just equal to the base area, so the area just of that base region times the height. So the height here is just 1, so it's the base area times 1, and so that's just equal to the base area. So in this way that we can see that if I just integrate 1, I get the area of D. So if I ever notice that I have some double integral where the function is just 1, I know this is just the area of the region. So if we can find the area of the region, we can just say that the integral will equal that area, and we don't actually have to do out the integration. So let's try that. What are we actually evaluating here? My y is going from y equals the negative square root of 9 minus x squared to positive square root of 9 minus x squared. That's the one we just saw in the last example. That's going to give us that bottom half and top half of a circle of radius 3. Y equals negative square root of 9 minus x squared, square root of 9 minus y squared, x squared. And then my x goes from negative 3 to 3. That tells us we get the entire circle. If they said that x went from something like 0 to 3, then I would know I would just have half of it. And so I get this region. That's a circle of radius 3. So the area is pi times the radius 3 squared. And so that whole thing is just 9 pi. And so I can evaluate that integral just by using the geometry. I don't need to do any special integration there. Okay, let's try a few more examples. Let's say D is the triangular region formed by the points 0, 0, 2, 2, so I'll just call that 2 and 2, and 3, 0. So this is my triangular region. And I want to set up the integral of double integral of 1 minus y squared. So I'll put that in there. And I can decide if I want to do a d type x or type y. If I look at this, I notice if I try to do a type y, if I'm moving parallel to that y-axis, the bottom's always going to be 0, so that's nice. But sometimes when I leave along this left-hand curve or line, and sometimes when I leave along the other one. So if I color them, right, I would have this blue curve and this green curve. So sometimes I'm going 0 to blue, and sometimes I'm going from 0 to green. And so I'd have to use two separate integrals. So I'll show you what that looks like to set up. But first, I'm going to do a type x integral. I'm going to move parallel to that x-axis, because that's going to allow me to set this up with just one integral. Okay, so let's do that. I'm going to do my x first. I'm moving parallel to that x-axis. I notice the first curve I hit on that left-hand side is the blue curve. And then the second one I hit is that green curve. So I just need to go from the blue curve to the green curve for my x bounds. And then for y, I'm just looking at points. So the lowest point that I'm looking at on that y-axis is 0, and that highest point is 2. So now we just need to find equations of that blue curve and that green curve. The blue curve goes from 0, 0 to 2, 2. So I can say, okay, its slope is change in y over change in x, so 2 over 2, which is 1. Its y-intercept, I can easily see, is just 0. It's going through the origin. And so it's the line y equals x. And so the blue curve in terms of x equals is x equals y. So we can put a y down there. Remember, that's x equals y. The green curve is a little bit more complicated. It has a slope of, goes down 2 over 1, so 2. If you kind of follow it, you could follow it back over to find the y-intercept, or I can just plug in a point. So I can say its point is, let's use 3, 0. So I get y minus the y value equals slope, x minus the x value. So y equals 2x minus 6. Let's double check that we did it right. If I plug in 3 for x, I get 0. If I plug in 2 for x, ooh, I get negative 4. What did I do? Oh, negative 2 slope. There we go. Yep, it's definitely going down. See, it's good to check. Good to check your work. Okay, I think I fixed it. When I plug in 3, still get 0. When I plug in 2, I get 2, 2. Great. Okay. So that's my y equals. I need it to be an x equals because it's dx form. So I get y minus 6 equals negative 2x. And so x equals negative 1/2 y. And then I'm dividing both of them by negative 2, so that becomes plus 3. And so I get 3 minus 1/2. Oops. 1/2 y. And the y is upstairs, up there. Okay. And so that's going to be my bounds there. I'm just going to box that final answer so you know what part is extra and what part is my final answer. But let's go ahead and be a little fancy here, and we're going to do the type y as well. So we don't have to do that. I wouldn't recommend necessarily doing it if you don't have to, but I think it's good for practice. So if I want to do a y first integral, if I'm moving in the direction of the y-axis, the first thing I hit is this black curve down here. And sometimes I go to blue and sometimes I go to green. So I actually need two separate integrals. So I'm just going to start out by writing my two separate integrals. And what we're going to do is we're going to add those two integrals together. And so I notice that I always start at 0 in terms of the y-axis. I go from 0 for the bottoms on both of them. And then on one of them, the top, the upper bound is that blue curve. So that's y equals x. But on the other side, so over here, let's see if I can kind of highlight these differently. I've got this yellow region, and I've got this, I'm trying to pick a good color. It's different than the colors we've used. Maybe we'll make it red. We've got this red region. So in the yellow region, that's the one where I'm going to go from 0 up to the blue curve. But then in that red region, I'm going from 0 up to that green curve. And we already found, oops, let's finish back here. We already found that equation was y equals negative 2x plus 6. And then when I'm looking at my x bounds, the yellow region goes from x equals 0 to 2, and then the red region goes from 2 to 3. So we can set that up as a type y. Well, it's not technically type y because it took 2, but I can still do it as y first, even though it's not type y. And then I plug in my equation for both of those. Okay, here's one for you to try. We want to switch the order of integration on this. So I encourage you to go ahead, take a second, pause the video, try this one out on your own, and then come on back and see if you got the same thing as I got. Okay, if you haven't paused yet, I definitely encourage you to do that. I'm going to go ahead and talk through what I got. So I'm going to switch the order of integration. So I always like to first draw out what we get. So I have x equals 1/8 y squared. If you like to draw in terms of y equals, we can just solve for y. We're going to have to do that anyways. So let's color code this. We'll keep this one in black. So we get 8x equals y squared, or y equals the square root of 8x. So I'm going to draw something that looks like a square root function. And then I also have x equals root y. That's the same as y equals x squared. They're going to run into each other. And we can check. It looks like my guess is that they're going to run into each other at this upper y bound, y equals 4. If I plug y equals 4 into my top bound, square root of 4 is 2. I plug it down here, 4 squared is 16 divided by 8 is 2. So it is true. When y equals 4, x equals 2 for both of those. So I do know those, and I can kind of use that as a hint. And so again, we're going from x equals my 1/8 y squared to x equals root y, left to right, my left one, and my right one. Okay, so now that we have it drawn out, we know exactly the region that we're trying to integrate. In between those, I can change it. So I'm going to change my integral here. We'll do y first. Doing y first, I'm going bottom to top. The bottom curve is that blue curve, which I already solved, is y equals x squared. The top curve is that black one, so y equals root 8x. The function stays the same. And then for my x bounds, I'm just looking for points. So I go from 0 to 2. 0 to 2. Oops. All right, let's do one more example here. I want you to find the volume of the region in the first octant between the plane x plus 2y plus 3z equals 6 and the xy plane. So what is this going to look like? We often have these questions where we're talking about these planes in the first octant. So I'm going to give you a little shortcut on how to graph this. What I do is I just think of my intercepts. So I think, right, what happens when y and z equals 0? I plug in y and z equals 0. I get x equals, oops, I didn't draw an x. X equals 6. So that tells me along the x-axis, that's when y and z is 0, I'm all the way out at 6. When x and z is 0, I get 2y equals 6, or y is 3. So along the y-axis, I'm at 3. And then when x and y are 0, I get 3z equals 6. So z equals 2. And so that's z, not a 2. I know that my plane is going to go through those 3 points. And that kind of allows me to get my nice little picture in there. So I'm trying to find the volume sort of underneath this triangle in that xy plane. To find the volume using a double integral, remember you're going to integrate the surface. So I need to integrate that function. That's how we're going to find volumes. So I need to integrate. Oops, that's not a pen. Do the integral of the function, but I need it to be in terms of z equals. So I'm going to take this function here, and I'm going to solve it in terms of z equals. So I'll do it in kind of 2 steps. That whole surface is 3z equals 6 minus x minus 2y, or z equals, dividing by 3, 2 minus x over 3 minus 2/3 y. So I've got the function 2 minus x over 3 minus 2/3 y. That's my z equals function. And I have to integrate that. We can do either x first or y first. I'll do y first and then x, say. Okay, so what's the region I need to integrate? Well, I need to think about what's happening in the xy plane, what's sort of below that plane in the xy plane. So I'm going to extract that out. I notice that I have, in that xy plane, I'm crossing the x-axis at 6 and the y-axis at 3. So that region that I've highlighted is the region right here in the xy plane. That's my region of integration. And so that's the region that I need to integrate. I decided to go y first, so I'm moving in the direction of the y-axis, bottom to top. That bottom line is that line y equals 0, so I've got a 0 on the bottom. And then that top line, as I'm leaving my surface, is going to be, I'll highlight it in blue, this line here. The slope, I'm going down 3 over 6, so negative 1/2. Y-intercept, I can see from the picture, is 3, so that's just going to be y equals negative 1/2. That's not a half, 1/2 x plus 3. I can double check. I plug in x equals 0, I get 3. I plug in x equals 6, I get 0. And so that's that top curve, 3 minus 1/2 x. And then my x bounds are just the points 0 and 6. And so that's, if I integrated this out, which I will leave for you all to do, you'll get the volume of that region. Hope this video helped kind of give you some ideas about how all these problems work. Definitely reach out if you have questions.